Hello everyone. We're going to talk about the preliminary test for cations, the flame tests, the charcoal block reduction and charcoal cavity test, the borax bead reaction or borax test, or the phosphate bead test. We're going to also talk about the ammonia test. In the coloration test, first you detect the color of the ions. Some ions are colored while some are not. Some are, when in the presence of certain ions or when they are heated, produce certain colors. For example, the physical examination, you see that copper, anytime you see a bluish green salt, you know that it's copper, or a light green is ferrous salt. A dark green, it's, you know that there is presence of chromium salt, while dark brown is ferric salt. Light pink, you know that this is manganese. But when the salt is white, you know that all these colored salts are absent. You can decide to undergo the flame test to see the color change and confirm the presence of a particular ion. As I discussed in the class, different elements emit characteristic colors when introduced into a flame, allowing for identification. The principle is based on the fact that when certain elements are introduced into a flame, they absorb energy and emit characteristic color due to electronic transformation. Certain cations like group 5 radicals, barium, strontium, and calcium, in the form of their chlorides, impart characteristic color to the non-luminous flame. The chloride of these cations are thermally ionized. The ions so formed absorb heat energy and get excited. The extra energy is released in the form of light of the characteristic color in the visible part of the spectrum. Since different metal ions emit light energy of different wavelength, the color imparted by the different cations to the flame are also different. Now, what happens, how you do this test is you make a paste with HCl on a glass and you use a platinum wire, just as in the video. You watch the next video, you see that video I uploaded, you see how this is done, and you put it in the non-luminous flame and see the kind of color it emits, and each color has its own characteristic color. You see, like sodium has golden yellow, potassium emits violet color flame, strontium crimson red, calcium brick red, barium light green, copper bluish green or blue colored flame, zinc gives a flash of green, and so on. So each one has its own characteristic color. The charcoal cavity test or charcoal block reduction test. The cation is converted into metal carbonate in a charcoal cavity, which decomposes on heating to metal oxide or even to the metallic state. The cation present can be detected from the color of the bead or residue left in the cavity. Now, this residue is called incrustation. I uploaded a video also how the charcoal cavity test is being done. The procedure for this charcoal cavity test is you make a small cavity in the charcoal block with the help of a borer. Mix the given mixture with sodium carbonate. Moisten it with a drop of water. Heat in the charcoal cavity in the reducing flame with the help of a mouth blow pipe and observe the color of the residue left. Now, when the residue is, observe that it's shining, is a shining metallic bead with yellow incrustation. You know that this is lead. When you have a shiny metallic bead which does not mark paper, you know what this is. When you have brittle bead with yellow or brown incrustation, you also know that. When you have a white incrustation with white fume having garlic odor, you know this is arsenic. When you have brown residue and brown incrustation. So by the residue left, the incrustation left, you can be able to determine the presence or the type of cations that is present on the in the mixture. Borax bead test. This borax, also known as sodium borate or sodium tetraborate, or you call it disodium tetraborate, is a salt of boric acid. It is powdered is a white powder, and it's soluble in water. It consists of soft colorless crystal. This test is employed for the detection of cations in colored mixtures, which may contain copper, nickel, iron, or manganese. Now, the borax bead reacts with this metal oxide to form metaborates, which have characteristic color. Some metaborates, when heated in reducing flame, form lower metaborates or even metals, thus causing a change in the color of the bead. I have uploaded a video on the borax bead test, how it's been performed, and how the bead form, how it formed from for the transparent glassy bead is formed from borax powder, and so on. Look at the video, and it's the same procedure for the phosphate bead test as well. Now what you observe is when you put the bead in a reducing flame and in oxidizing flame, they produce different color for each cation. So each cation has its own characteristic color, both in hot and in cold in oxidizing flame, and also in hot and in cold in reducing flame. The phosphate bead test is similar to the borax bead test. This is also called microscopic salt bead test. It also forms a colorless bead. It's just that this is a sodium meta. Contains sodium metaphosphate. This combines with metallic oxide, forming orthophosphate, which are often colored. Thus, a blue phosphate bead is obtained with cobalt salt. The sodium metaphosphate glass exhibit little tendency to combine with acidic oxide. Silica in particular is not dissolved by the phosphate bead. When a silicate is strongly heated in the bead, silica is liberated, and these remain suspended in the bead in the form of semi-translucent mass. The so-called silica skeleton is seen in the bead during and after fusion. The reaction is employed for silicates. The color of the phosphate beads are more pronounced than that of the borax bead. In the table, you see the difference in color, the characteristic color they produce for each ion, both in oxidizing and reducing flame. The ammonium radical test is easily detected because of the sharp odor of ammonia, evolution of ammonia gas, and its action on moist red litmus paper to blue due to its alkalinity. This indicates the presence of ammonium salt.